Good evening, class. Today we're trying to do chapter 10, second half of chapter 10, which is derivatives. Okay, so this is the core of what we will cover for the rest of the semester. So today's the introduction, and then we'll dig deeper and deeper into it because this is the most useful part of calculus that you will encounter in economics over and over again going forward. So I hope you pay attention, and I hope you write down your questions if things don't make sense, and then let's definitely make sure we talk about it in class on Thursday. Okay. All right. So far up to this point in this chapter, we mostly have talked about limits, and then we started talking about the average rate of change. Now, with the second half of this chapter, the first thing in chapter section 10.6 is something called the instantaneous rate of change. Now, I don't like how this book is approaching this topic because the instantaneous rate of change is the slope of a function that's a curve at a certain point. And when we do that, then hopefully you already know at this point that the slope of any point on a curve is going to be the slope of its tangent line, right? A tangent line is a line that lies against a curve at one specific point. So now this slope is actually obtained through taking derivatives. So if you calculate the instantaneous rate of change, okay, you are really talking about the derivative. Okay, so I'm gonna excuse me. So I'm gonna just talk about the derivative, and then these things will make more sense because I don't like the approach the book takes. Okay, so but there is one thing I want to mention though. Your book also talks about something called the difference quotient. Okay, and the difference quotient is something that we will use, as you can see in a second, to calculate the derivative. Okay, the distance quotient says, well, if, okay, x and then f of x, or you can think of this as x and y, okay, is any fixed point on the curve, okay, and x plus h is any arbitrary number, then f of x plus h, so is another point. Okay, so this is x plus h, and then y calculated with x plus h plugged into the function for this curve, right? So then, okay, the quotient, the difference quotient okay, is the slope of the secant line through these 2 points. Okay, so it's expressed as, you know, the slope for the secant line, so SEC for the secant line, oops, okay, equals, just like how we calculated the average rate of change before, the y value, which is f of x plus h, minus f of x. Okay, so the difference in the y value divided by the difference in the x value. And you can see the denominator can be simplified a little bit because x plus h minus x is just h. Okay, so this is called the difference quotient. And now, to understand this better, like I said, it's best to just introduce the idea of the derivative, and then we can go back and talk about the instantaneous rate of change. So a derivative, okay, it's denoted for any function. So see, for any function, okay, y equals f of x, okay, the derivative of the function f at the point x, or the value x, is defined, okay, to be, it's denoted as f of x prime. Okay, so that's defined as the limit of fx plus h minus f of x divided by h as h approaches 0. Okay, so the derivative is really telling you what is going to, the change, the rate of change at point x. So as you leave x, even ever so minutely, right? Because here you can see this is the difference quotient in the parentheses here for the limit. And this is saying that, as you move from the point with a value of x and f of x, so, or x or y, x and y, as you move away from that point ever so slightly, okay, what does that trend tell you? And that is really what your derivative. So the derivative is, in layman's term, the rate of change, or what's going to happen next with this function. Okay, so we take this limit as h approaches 0. That means we're just moving away from that point ever so slightly. Okay, and then what does that function become? And then, or what does that limit become? And that is our derivative. Okay, so the derivative again is trying to tell you what is the rate of change from a certain point on a curve, or with a given function. Okay, so now let's see how we can determine what a derivative is, right? Because, well, there are three things, right? So first of all, we need to make sure we have this difference quotient that we can write out, and then we got to simplify this this expression, this difference quotient, algebraically, and then we need to calculate what that limit is if it exists, right? So let's look at an example, then you can figure out what the derivative is. Okay, so example, right? So let's say that you have f of x equals x to the cube minus 5x. Then I want you to find, okay, the derivative, or f of x prime, if it exists. Okay, now f of prime of x, okay, this is also the instantaneous rate of change. So we already talked about this, right? The instantaneous rate of change is your derivative. So just keep that in mind when you're calculating your derivative. You are calculating the slope of the curve at the point x and y, okay? Or the instantaneous rate of change of the curve at point x and y, okay? Or x and f of x, because we're assuming y equals f of x, right? So that's what we're always assuming. Okay, so now let's look at this specific function and say, okay, well, I know the derivative, or the slope of this line at point x and y equals the limit as h approaches 0 for f of x plus h minus f of x divided by h. Okay, so really it's the difference between the two y values and then divided by the difference of the two x values, and being x and y, then x plus h, and then f of x plus h. Okay, so let's plug this in, and this equals the limit as h approaches 0 for, okay, so this is x plus h cubed minus 5 times x plus h. We just replaced x from this original function here with x plus h, okay? And then minus, okay, x cubed minus 5x, okay? So that is what f of x plus h minus f of x equals to, then divided by h. Now you can see it's pretty complicated. We need to figure out how to simplify everything in the numerator. So let's then expand everything out, okay? So we know x plus h cubed equals x cubed plus 3h times x squared plus 3h squared times x plus h cubed. Okay, you can verify this by multiplying x plus h 3 times right next to each other. Okay, then we know this, then minus 5x minus 5h, okay, because I just multiplied this 5 into the parentheses. Okay, then minus x cubed, then plus 5x, because minus a negative 5x equals plus 5x, okay, over h. Now you can see we can cancel a few things out, right? Because h cubed, x cubed and x cubed cancel each other, okay, and then negative 5x and positive 5x cancel each other, okay? Then we have this equals the limit as h approaches 0 for 3hx squared plus 3h squared x plus h to the cube minus 5h divided by h. Well, you can see that since every term in the numerator has h in it, dividing by h means you're just canceling one h out of every term in the numerator. So this becomes the limit as h approaches 0 for 3x squared, because h in the denominator canceled the h out in the 3hx squared. So it becomes just 3x squared. Then the next term becomes 3hx, because again, originally you had h squared and then you cancel one out, plus h squared, okay, same reason, minus 5, okay? And that is what your original limit has become. And since this is a polynomial, so that means you can just plug in h equals 0 into this function for this, to calculate this particular limit. So this equals 3x squared plus 3 times 0 times x plus 0 squared minus 5, which just equals 3x squared minus 5. And this is your derivative for the original function right here. Okay, so given the original function of f of x equals x cubed minus 5x, the derivative is 3x squared minus 5. Okay, so that's how you define and calculate a derivative. Okay, now let's talk about some rules, some conditions, excuse me, for a derivative to exist, and then some rule of how to calculate a derivative more quickly instead of having to take a long calculation through the limit approach. Okay, so first of all, for a function to be, first of all, not all functions are differentiable, okay? Because that's how we when you can differentiate a function, that's how you get the derivative. Now, not all functions are differentiable, okay, at a given point, because one, f of x, if f of x is discontinuous, okay, at x equals a can be any real number, then that function is not differentiable, so you cannot take a derivative. Okay, two is if the graph of f of x has a sharp corner at x equals a, that also is not differentiable, right? So for example, well, let's change, instead of y, let's do f of x, right? So if you have a graph that looks like this, okay, this is where x equals a. This sharp corner means you cannot differentiate this function, okay? The function has to be continuous and smooth like this, or a straight line, right? Okay, so another possibility is if the tangent line, remember the derivative is really the slope of your tangent line at point x. So if the tangent line at x equals a is a vertical line, okay, then in that case, if it's vertical, the slope doesn't exist. If the slope doesn't exist, you cannot take a derivative of this function. So if any of these three things occur, then there's no derivative that can be taken for a function, okay? But other functions can be differentiated, okay? Now, just a quick review. We said a function of f is continuous at x equals a if and only if, okay, sometimes this phrase is expressed as IFF, okay, so if you see that, that means if and only if, okay. We said the limit of f of x as x approaches a from the negative side or the left side equals f of a by plugging a in for x, and that also equals the limit of x approaches a from the positive or the right hand side. So if this is true, then f of x is continuous at a, and then a derivative is possible. Okay, now sometimes you want to look at a function's continuity on an interval, okay? So you say the function f is continuous, okay, on an interval from x1 to x2, okay, if, okay, the function f is continuous at x equals a for every number a within the interval. So if a is any number between x1 and x2, and then at any of those points the function f is continuous, then we say the function f is continuous on the whole interval, okay? Now let's introduce the first rule for your derivative that will make your life a little bit easier, and we'll introduce more rules in future chapters, but this one is called the power rule, okay? The power rule says your for okay, f of x, any function that is f of x equals x raised to the rth power, okay, where r is a real number, okay, then the derivative of f prime x equals r times x raised to r minus 1th power. Okay, so the rule here really just says that you, when you take a derivative for a function with any power to the x can be 1, okay? I mean, so x itself is x raised to the first power, right? And x square root is x to the 1/2. So really this function is this rule is very useful because any x form will give you a power. So what you do is when you take the derivative of this function, okay, you can bring down the power of the x. So if we're talking about x raised to the, so f of x is x raised to the 1/2 power, or f of x is the square root of x, then f of prime of x, the derivative, is by bringing that power down, whatever it is. So you bring it down here first, make it multiply x, and then you take the original power and minus 1 out of it. Okay, so in this case, this equals 1/2 times x to the negative 1/2, or if you want to write this into a more recognizable form, this is negative means is in the denominator, and then 1/2 is the square root of x. So you can do 1/2 times the square root of x. Okay, so that's kind of the first and most useful rule for taking a derivative. And of course, given this rule, you can see when, f of x equals x, then that is, x raised to the first power. So f of x then equals 1 times x raised to 1 minus 1th power, which is 1 times x raised to the 0th power, and anything raised to the 0th power is 1. So that is 1 times 1, which is 1, right? So in this case, x will disappear and you'll get a constant. Now, if you're talking about a constant, right? So if f of x, so let's do some examples. Okay, if f of x equals 5, really this is saying f of x equals 5 raised to, I'm trying to think if I should introduce, introduce this idea at all. Never mind, let me just give you this as a rule instead of an example, okay? So, two special cases of the basic rule or the power rule, okay? So first of all, if f of x equals c, which is a constant, okay, then the derivative is 0. The derivative for any constant is 0 because we said, remember, the derivative is the rate of change at that point. Well, but if the function is a constant, then the rate of change is 0. It's not changing, right? So hopefully that's easy to understand. And 2 is if f of x equals x, then f of prime x is 1, okay? That means the slope for your derivative has, a slope of 1, right? So these are some special cases, okay? And then also, okay, if you have a polynomial function, okay, and then your f of x is continuous everywhere, right? So if you have a function that is like this, right, a0 plus a1 x plus a2 x squared plus dot 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 plus an xn, right? So this is a polynomial form, and where a0, a1, a2 through an, those are real numbers, okay? And your exponents are all positive integers. So you go from 1 all the way to n. 1 through n is all positive integers. If this is the case, okay, then f of x is continuous everywhere. So you can take a derivative for the entire domain, okay? All right, now an extension of the power rule. Okay, so again, this is the general case. This works. So if f of x equals some constant times x raised to the rth power, okay, then I should say if then, okay, f of x prime is the constant times bringing r down here times x raised to r minus 1th power. So the constant will simply carry over into the derivative, okay? All right, so knowing all these rules, let's look at some examples to practice. Again, I want you to pause the video, do it on your own, then compare my answers with yours and see if you get the same thing, right? So first of all, if f of x equals 8, okay, and this is a constant, so we know then the derivative is 0, right? Because there's no change. This line is just flat all the way through, okay? Now, what if f of x equals 5 times x to the cube? Well, then the derivative is 5 times, you bring the original power for x down, and then this times x with the original power minus 1, so which is 15x squared. Okay. Now, what if f of x equals the square root of x? We already did this one, right? So we said this one is, and this equals x raised to the 1/2 power. So this equals 1/2 times x, the original power minus 1, which is 1/2 times x minus, negative 1/2, right? So now, similarly, okay, what if you have f of x equals 1 over x? That is x minus 1, right? So f of x prime in this case is negative 1 times x negative 1 minus 1, which is negative x negative squared, or another word, negative 1 over x squared. Okay, so these will take some practice, but you can get this pretty quickly. Okay, let's do one that's slightly more complicated, right? So what if, okay, we have, okay, f of x equals 18 divided by x raised to the 2/3 power. Okay, well, again, this equals 18 times 1 over x raised to the 2/3 power. And when the x is in the denominator, then we know this equals 18 times x raised to the negative 2/3 power, right? The negative power means it's 1 over something. So now we can do f of x equals 18 times negative 2/3 times x negative 2/3 minus 1, which gives you, okay, so negative 2/3 times 18 is negative 12 times x, then negative 2/3 minus 1 gives you negative 5/3. Okay, so, or if you want to write it into a form that's similar to the original function, this is negative 12 over x raised to the 5/3. Okay. All right. So I hope that's some good exercise for you to understand what the derivative is, which is the rate of change at any given point on a function. And it is taken by, it's calculated by taking the limit of moving away from that point ever so slightly. And then we came up, but we did a power rule that is giving you a good tool to get started with calculating the derivative without having to take the limit every time. Okay. All right. Now, okay. So another way that we can express the derivative, because often we say we let y equals f of x, so you have functions with y in it instead of f of x. So in that case, instead of having f of x prime as the derivative, another way of writing it is dy dx. Okay, so this is saying you're taking the derivative of y with respect to x. Okay, so this is the same as f of x prime. Okay, so now as a general rule, okay, if y equals some constant times a function, okay, so in this case it was 1 times f of x before. Now if it's a bigger number than 1 or whatever different number than 1, then dy dx equals c times f of x prime. So you can keep that constant and just take it out and take the derivative of f of x and then bring them together. Okay, and similarly, okay, so this is the constant times the function rule. So this is a constant times a function rule. Okay, similarly, we have the sum and difference rule, where we say, okay, and if f of x and g of x are differentiable functions, and y equals f of x plus or minus g of x, either way works, okay, then dy dx equals f of prime x plus or minus g of prime x. Okay, so this is saying that if y is the sum or difference of two different functions that are both differentiable, then the derivative y is then the sum or the difference of the derivatives of those two functions. Okay, remember that the derivatives come from limits, and limits are very flexible in terms of being manipulated, right? The sum of limits, the limit of a sum equals the sum of a limit. The difference of the limit of a difference equals the difference of limits. So that's how this got carried over. And we'll introduce again more rules as we go on, but these are things to keep in mind. Okay, so let's do some exercises. Okay, again, examples. Okay, so let's say we have y equals 5 times x squared, then that means dy dx equals 5 times 2 times x raised to the first power, and you don't have to write the first, so that gives you 10x. Okay, and what if y equals negative 4x? Then dy dx is just negative 4. Then you can do times 1 and then times x raised to the 0th power, which then goes to 1. So that is still negative 4. Remember, you can just take the constant in front of the x in that case. Okay, what if y then equals the first two combined right here, right? So what if this equals 5x squared minus 4x? Well then, without having to calculate, you should know this equals 10x minus 4. Okay, these two, since the function now is the sum of the previous two functions, then the derivative, whoops, sorry, not that. So then dy dx equals the derivatives of the two previous functions added up together too. Okay. All right, one more. We'll say, what if y equals x to the third plus 8 times x square root plus 2 over x? Okay, how do we do this function's derivative? Again, these are just sums of a bunch of simple derivatives. Okay, so we just need to take the derivative of each one and add them up. Okay, so again, to help you see more clearly, I'm going to change these into x with their specific powers so you can see. But this is x cubed plus 8 times x raised to the 1/2 power plus 2 times x raised to the negative first power, right? So well, that is what this function equals to. So then dy dx is 3 times x squared, right? You bring down the power and then minus 1 out of the power, okay, plus 8 times 1/2 times x to the negative 1/2, because 1/2 minus 1 is negative 1/2, plus 2 times negative 1 times x raised to the negative second power. So this equals 3x squared plus 4x to the negative 1/2 minus 2 times x to the negative squared. Or if you want to express it closer to the original form, this is 3x squared plus 4 over the square root of x minus 2 over x squared. So okay, again, we'll have plenty of practices for you. Okay, so now let's do a little bit of more algebraic manipulations. Okay, so let's look at another set of examples. Okay, so let's say, what if f of u equals u raised to the 1/2 power times u squared plus 2u. Okay, and what is f of u prime? What is the derivative? Well, now let's again look at this a little bit more. So this equals u raised to the 1/2 power times u squared plus u raised to the 1/2 power times 2 times 2u, right? Now, if you recall, in the past, we have said x to the raised to the 8th power times x raised to the bth power equals x raised to a plus bth power. Okay, so that is a rule that we have learned a long time ago from algebra. So then this becomes u raised to the 5 over 2 5 seconds power plus 2 times u raised to the 3/2 power. Okay, because you're just adding these powers together. And remember, 2u is 2u raised to the first power. That's where that 2/3, the 3/2 got, where we got that. Okay, so now then the f prime of u equals, then you bring the power down, then times u raised to the original power minus 1. So that becomes 3/2 plus, okay, 2 times, you bring the power down, then raise it to u, the original power minus 1. So it's 1/2. And then this is 5 over 2 u 3 seconds plus 3 times u 1/2. Okay. All right, let's do another one. It says, what if f of v equals v squared plus 1 divided by the square root of v, and then find f of v prime. Okay, so again, we want to manipulate this a little bit. We say, okay, well, this equals to v squared plus 1 times, okay, 1 over the square root of v is v raised to the negative 1/2. Negative means it's in the denominator. 1/2 is the square root of it, right? So then we just do v squared times v raised to the negative 1/2 plus v to the negative 1/2, right? Because that's just multiplying the v raised to the negative 1/2 through the parentheses. And again, v squared times v raised to the negative 1/2 equals v raised to the sum of these two powers. So that gives you 3 seconds, right? Plus v of negative 1/2. So once we have here, then we can do f of v prime equals, then you just bring the power down as a coefficient, then times v raised to the power minus 1. So that's 1/2. Plus negative 1/2 times v negative 3/2. All right, so this gives you 3 seconds v 1/2 minus 1/2 times v negative 3 seconds. Okay, so again, I hope that makes sense. Okay. Now let's take this a little bit more complicated, okay, and try to tie a few things together. Like I said, this is the very basic concept of what derivative is, and the most useful and common rule, the most basic rule about how to take a derivative. That's what we're introducing here. The next chapter will introduce a bunch of other tricks and rules that you can use to manipulate things with. Okay, so let's say you have a function f of x equals 8x minus x squared. Okay, now I want you to find the slope of the tangent line at x equals 2, x equals 4, and x equals 5. Okay, so hopefully by now, once you see that you're looking for the slope of the tangent line, you know that we're supposed to take the derivative of this function and then plug in these different values, right? So first, let's take the derivative. F of prime x is 8 minus 2x, right? And so once we have that, then we know the slope. Okay, so at x equals 2, the slope is f of x prime equals 8 minus 2 times 2. Oops, 8 minus 2 times 2, which is 4. So the slope is 4 at x equals 2. Okay, at x equals 4, then the slope is 8 minus 2 times 4, which is 0. That means the slope there is, it's or the function there is no longer changing in one direction. Okay, then at x equals 5, the slope is 8 minus 2 times 5, which is negative 2. So you can see this function at x equals 2, the slope is positive, means it's rising, it's positively sloped. Then at x equals 4, it's 0. That means at that point, the tangent line is flat. Okay, and then at x equals 5, it's a negatively sloped curve. So you know this function goes like rising until it hits x equals 4, which it hits the top, and then it starts going down. Okay, so in the future, we'll talk a lot more about the significance of these turning points on a graph, because these turning points, whether it's turning from up to down or down to up, gives us either the maximum or the minimum of a function. And you might not be able to see it just yet, but we care a lot about these points because we want to often figure out cost minimization, right? If I have a cost function, where is my lowest cost point? Or profit maximization. If I have a profit function, where do I find the highest profit I can obtain? And this is exactly how we find it, using the derivative, which is the slope of the tangent line, to find where it equals 0, right? And that gives us those maximum and minimum points. So then we can identify those points a lot easier than trying to do those through algebra. Okay, so that's just kind of a little preview of how this can be used. Okay, now the second question is I want you to find the equation of the tangent line. Okay, at x equals 2, x equals 4, and x equals 5. Okay, so the equation for that tangent line is not the same as the slope of the tangent line. The slope is the derivative of f of x, but the equation, we need to go back and remember something, right? Because we said, okay, one of the functional forms, or the forms of equations we know, is y. So if you know, I should say, okay, if you know a point goes through x1 and y1, that's, you know, if a line goes through that specific point, then and you know the slope is m, then the equation for that line can be written as y minus y1 equals m times x minus x1. Okay, this is the point and slope method of finding the equation of a line. We talked about that several weeks ago, so this is a quick review. So to find the equation of the tangent line, then first of all, we need to know what the y values are for these different three x's. So we say when x equals 2, then y, or f of x, equals, okay, we have to use the original function right here, okay? So that equals 8 times 2 minus 2 squared, which is 16 minus 4, which is 12. So at that point, okay, then the tangent line at the point of 2, so x is 2, y is 12, and is y minus 12 equals the slope of this line, which is right here, 4, equals 4 times x minus 2. Okay, because here x1, y1 is 2 and 12. That's the x and y value for that point. Okay, once you know that, and you know the slope from the derivatives, then you know this is the functional form for your tangent line. Now you can change it into the standard form if you want, or you can leave it like this. I don't care either way, as long as you do it right. Okay, so at x equals 4, okay, now the y value, or f of x, is 8 times x, which is 4, minus, okay, x squared, so 4 squared, that gives you, okay, 32 minus 16, which is 16. And so that means the point when x equals 4, so the point is 4 and 16. Okay, so your tangent line function then is y minus 16, okay, equals the slope, which is 0 right here, right? So 0 times x minus 4, the x value here. And that just equals y equals 16. So we expected this, right? Because this is a function where the slope is 0. So it has to be a horizontal function. A horizontal function takes exactly this form, y equals some constant, right? So because y equals a constant from point to point, there's no change. So the rate of change, which is the slope, is 0. Okay. Then finally, at x equals 5, f of x is 8 times 5 minus 5 squared, which is 15. Okay, so the point then is 5 and 15. So your tangent line function is y minus 15 equals the slope of -2 times x minus 5. Okay, so that's the tangent line at point of 5 and 15 when x equals 5. Okay, so this is kind of tying the whole tangent line idea, the slope idea with the derivative, and then how to express the function of a straight line, because tangent lines are all straight, using the point and slope method. Okay, so hopefully that helps you figure a few things out. Then finally, excuse me, the last section in this chapter is about applications and specifically about marginal analysis. Hopefully you get excited about it because marginal analysis is a huge part of economics, right? Marginal cost, marginal revenue, and then we have, in other concepts, marginal product of labor and the marginal rate of substitution. So a lot of analysis we do in economics is marginal analysis, and that's where your knowledge on derivatives can really come in handy. Okay, so in the past, okay, we said your marginal cost equals the change in total cost over the change in quantity, right? And now you should know this is really D total cost over D quantity. Okay, so this is really taking the derivative, the total cost function, with the respective quantity, and that is what marginal cost is. So marginal cost or marginal anything is the derivative of the total function. So marginal cost is the derivative of the total cost, and marginal revenue is the derivative of the total revenue function. Marginal product labor is the derivative of the total product function, right? So all these marginal analysis hopefully now will seem straightforward. So let's look at an example. Okay, so let's say that you have a cost function, c of x equals 500 plus 3x, where x is quantity produced. So usually we call x Q in economics, but here, since we've used x so much, let's just stick with x. Okay, so now if I were to ask you, what is the marginal cost of producing the 110th pen? So marginal cost of, so this is, the quantity of, let's say pencils produced. So marginal cost of 101st, okay, pencil. Now, with your traditional way, you say, okay, the marginal cost of 101 is the change in total cost, which is total cost from producing 101 minus the total cost of producing 100 divided by the change in quantity, which is 101 minus 100. And that is the case. In this case, we plug 101 into your total cost. And so that is 500 plus 3 times 101 minus 500 plus 3 times 100 divided by 1. And if you do all the math, you'll see this is $3. Okay, so it costs $3 to make this fancy pencil, the 101st fancy pencil. Now, given this knowledge of derivatives, you can say, well, okay, the 101st pencil's marginal cost is, I take the derivative of this cost function, and if there is still a x, I'll just plug 101 in, and that will give me the answer. So you just take the derivative of c of x, and that equals 500 is a constant. The derivative of that is 0 plus 3x. The derivative is just 3. So that means it's 3. So this tells you, hey, every pencil you produce will cost you $3. It's a constant marginal cost. So the 101st one is going to be $3. Okay, already done. If you have a more complicated cost function and the derivative turns out to be a function of x, then that's when you just plug 101 into that x in the derivative function and you'll get the marginal cost, which is a lot easier than doing all of this and making math errors in the process, right? So hopefully you can see the convenience in that. Okay, so similarly, if you remember, marginal revenue equals the change in total revenue over the change in quantity. Now it's just, the derivative of the total revenue function over the derivative of quantity. And again, usually we don't, here we use x for quantity. So let's look at an example. Okay, so let's say that if you're a producer of tables, okay, and you have a demand curve, demand function, which is the price equals, okay, the demand function of 117 minus x over 4, where x is quantity produced, or just, let's say, just quantity, produced. Okay, so that is your demand function. Okay, and now I want to ask you, first of all, find your revenue. Find the revenue function. Okay, so hopefully you remember, well, let's say this is R of X. Revenue is price times quantity, and quantity here, whoops, what happened? Quantity here is X, right? So that means it is 117 minus X over 4 times X, right? Because price is expressed in the demand function by 117 minus X divided by 4. Okay, so price and quantity are related. Okay, so this gives you 117 times X minus X squared over 4. Okay, that is your revenue function, because that's what you get by multiplying price and quantity together. Okay, and that gives you your revenue, which is how much money you're bringing in. Okay, so that's the easy part, right? B is, well, okay, then find marginal revenue when X equals 16. So what is the marginal revenue when you make the 16th table? Okay, so how much will the 16th table bring you? Okay, well then we know that marginal revenue is really the derivative of the total revenue function, and that is 117 minus, okay, 2, let's do 1/2 times 2 times x, right? Because this term is 1/4, not 1/2, sorry, 1/4 times x squared, and then you just bring the squared term down and to be the coefficient, and then subtract 1 from the power. So this gives you 117 minus 1/2 x. That is your marginal revenue function. Okay, so once you have that, then at your marginal revenue, or I should say marginal revenue equals, this, and at x equals 16, marginal revenue then equals 117 minus 1/2 times 16, which is $109. That means the 16th table will bring you $109 in revenue. Okay. All right. Now, of course, your marginal profit, okay, is the profit every unit, every product brings you. So if you have a total profit function, right? So profit function is total revenue minus total cost, okay? And then your marginal profit, okay? Just do marginal profit, okay? It's the change in total profit over the change in quantity, or now you know is the total derivative of the profit function over, I mean, with respect to quantity. Okay, so that is how we use it in economics. Okay, and you know, this of course just equals d of total revenue function dq minus d of total cost function dq, right? So so I don't think you need necessarily more examples. As long as you know this, then you can figure it out. Okay, so that's the second half of chapter 10. I hope you guys do a lot of practice to understand. So at this point, the examples and the homework questions are still fairly easy. Using just that one power rule, you can solve all of them. But as we go on, we have a lot more other rules to introduce, and the functions will become a lot more complicated to take the derivative of. But you know, for now, I want you to understand what a derivative is, which is the rate of change at any given point on a curve. The curve, of course, is representing a function, and then it's calculated by taking the limit of going from that point to a different point as that distance approaches zero. Okay, and then of course, once we establish that with the rules we'll continue to introduce, you'll never really have to take the limit and do the tedious calculation to take the derivative. With the help of the rules, most of the time you can find some rule to help you cut the corners and calculate derivatives fairly easily. And then the application, of course, is heavily used in economics, and especially finding the maximum or minimum points on a function, which is what we often look for, right? So we'll talk about how to find those as we go on. So anyway, this is the end of the video. I hope you have found it helpful. Again, write down all your questions and let's talk in class. Okay.